Okay.
So, welcome everyone. I think we can get started now. Today we have another two presentations. This time we're going to focus on two papers regarding DRAM disturbance. And Harsh is going to introduce the first student.
All right, so today's first presenter is Kim Farney. He will present flipping bits in memory without accessing them, an experimental study of DRAM disturbance errors. Kim Farney is a master's student in DTED, and he particularly focuses on chip design and security in his master's. He took this course so that he can also dive into more topics beyond these as well as these, and which makes us a very good fit for what he wants to pursue. So the stage is all yours.
Okay, thank you. So the paper I will be presenting was first presented and published at ISCA in 2014. So the information here is already well known in research circles. And what we will look at first is some background. Then we will go over what disturbance errors are. Then we will look at some experimental testing and the results that the paper has gathered. Then the paper proposes a few solutions that we will look at. And finally, the paper's conclusion. After that, I will discuss what I think are the strengths and weaknesses and the discussion part with you guys. So first, for background, this is what a standard DRAM cell looks like. You're probably all familiar, but we will refresh some of this information. So there's a capacitor and a transistor in every cell, and the cell is connected over the rows with a word line and over the columns with a bit line. So in an array, this looks like this. Each individual cell connected in an array such that all the rows share a word line, and then all the bit lines go into a row buffer for reading and writing. So of course, this is embedded in an even larger structure for DRAM, which is this structure. So first, of course, we have the CPU, which has a memory controller, which interfaces from the CPU side with the memory. And then on the memory side, we have the DRAM module, which has multiple ranks, each of these ranks containing multiple chips, each of these chips containing multiple banks, and the bank contains what we have already seen previously, these arrays of cells. Okay, so for the structure of DRAM, as I've said, this leads to increased parallelism thanks to possible concurrent accesses over all the different banks, and leads to memory being quite fast nowadays. So further, how is memory accessed? We have several operations. We can open a row. This is called an activation, or ACT for short. Then we can read and write to and from the columns once the row has been activated. Then we can close the row again. This is called a pre-charge or pre. And then we can refresh the row. This is called a ref. So refreshing in particular is a mechanism that is necessary because the cells leak charge over time due to several electrical properties and need to periodically renew this charge. So for DDR3, the RAM generation that was observed in this paper, that was at the time of this paper the newest one, this is every 64 milliseconds. Now, the problem is, with disturbance errors appearing, that the DRAM is getting more dense. With the DRAM getting more dense, the cells are more tightly packed. With the cells being more tightly packed, they may electrically interact with each other when memory is being accessed. And this leads to disturbance errors in neighboring rows in the form of flipped bits. Now, usually these flipped bits go from electrical 1 to electrical 0. But since memory is not always stored the way that an electrical one is also a logical one, these can be any type of flip bits. The paper has tested these disturbance errors on real systems first. So they've used Intel and AMD CPUs and a 2 GB DDR3 module, and they have tested 2 bits of code. The 2 bits of code that they have tested to figure out if these disturbance errors appear on real systems are displayed here. Let's go over these code bits step by step. So first, in both sections, 1A and 1B, some rows are accessed with this move command. The addresses of each are X, and in code example 1A, also Y. So you can see the difference is that code 1A accesses 2 distinct locations in memory, while code 1B only accesses 1. Then the next operation, the CL flush, flushes the cache so that if these rows were cached, they will be flushed. So the next time this code is repeated, because both of these are loops, the loop will again access the memory directly. This is very important for this to work because we want to actually access the memory and not just mess around with the cache. And then there's an amp-fence operation, which is in place to make sure that the CPU doesn't optimize away any of this code and correctly executes it the way that it is also written here. After that, of course, the loop will jump back up to the start and just repeat this code all over. Now, as you can see here, the results produced errors in only one of these examples. Only code 1A induced errors, while code 1B did not induce any disturbance errors. This is, of course, because word line toggling leads to these disturbance errors. That was one of the first findings in the paper. Word line toggling refers to not the read and write part, but the activation and pre-charge part. If that gets repeated all over, the actual voltage of the word line fluctuates, and that is what leads to these errors. If you just access the same memory location as is done in code 1B, it doesn't induce errors because what the memory does, it only activates that row once, and then it just keeps reading and writing to it. And then at the end, it pre-charges once. So there's only one activation at the start and one pre-charge at the end. So there's no word line toggling. The word line is just on completely, and that does not induce any errors. They have then performed a lot of experimental testing to make sure that that wasn't just a faulty DRAM module or an isolated occurrence. So they have used an FPGA platform for this testing. They've used 8 FPGA boards, each of them programmed with a DDR3 800 DRAM controller, each of them also programmed with a PCIe 2.0 core. And they have tested 129 DRAM modules from containing 972 chips in total from 3 different manufacturers. The manufacturers will further be referred to as manufacturers A, B, and C because of anonymization. And they have used manufacturing dates varying over 5 years. So all of these modules are DDR3, but produced over a span of 5 years to ensure that it wasn't just an isolated incident again. They have tested these chips at 50 degrees Celsius, also tested at 30 and 70 degrees to, again, have wider testing. And they have tested an array of refresh intervals, which we've already looked at, is normally 64 milliseconds, but can be customized. So they have tested both higher and lower refresh intervals and activation intervals. Activation intervals here refers to how often they perform this word line toggling, at which interval. So that will be considerably lower than the refresh interval. We will see what exactly they use later. So for their first results on this table, you can see of the 129 modules they tested, many of them have produced errors. 110 of the 129 in total. And more importantly, after 2012, every single one, with the exception of this little guy right here, have produced errors. So there is a trend that is alarming, because if these errors appeared at some point and just start getting more and more widespread. It's a serious industry-wide issue. They have tested this at multiple refresh intervals, as I have said. So here you can see the refresh intervals. 64 milliseconds highlighted here is the standard refresh interval, and at that one, all three manufacturers in the different colors displayed here have had significant errors. However, as you may note, the errors also still appear at obviously at higher refresh intervals, but also at lower refresh intervals, and they only disappear at around a quarter of the standard refresh interval, which is a considerably faster amount of refreshes and would somewhat impact the performance of the module, because whenever the DRAM is refreshing, it cannot be accessed for read and write. So the disturbance errors appear at and below the standard refresh interval, and it's not just an isolated incident of having a weird refresh interval. Then the activation intervals they used, as you can see here, they had the most success, which you may can think, at low activation intervals. So they used 55 nanoseconds as their fastest one. And from there on, there's a somewhat linear decline in errors if they refresh, if they activate less consistently, less fast. But activation interval of 55 nanoseconds is completely normally achievable by a user level program. So this again indicates that more activations lead to higher error rates, and the activations are still at a reasonable amount that could be done by anyone using this machine. They have also tested which rows are affected by this disturbance. So the row 0 here would be the aggressor row, and then the numbers at the bottom indicate which row, how far away the rows are that are being flipped, where bits are being disturbed. So you can see here, most of the disturbances appear at exactly neighboring addresses. It's important that these are, of course, addresses that the system has access to, addresses that they use for the code, which do not necessarily correspond to the actual physical adjacency of these arrays, of these rows. And as you can also see, while it stays within -1 and 1 mostly, it does have a wide reach in these address spaces here. Again, doesn't need to mean that it is actual physical distance that is being covered over rows. They also discuss this in the paper, that it is possible for it to just all be rows that are directly physically adjacent, but they don't really know. They have also found multi-bit errors, which they categorize as errors that are more than 1 bit within a 64-bit word, which is an issue because common error correcting codes would work on 64-bit words, but can only detect up to 2-bit errors and can only fix up to 1-bit errors. So everything from 2 bits and above is an error that can no longer be fixed by error correcting codes or by the standard error correcting codes used commonly, and everything above 3-bit errors cannot even be detected anymore. There were 2-bit errors on all manufacturers and up to 4-bit errors within a 64-bit word for one manufacturer. They have also performed some further testing, which I will not present here for brevity, but they have tested several data patterns for the memory, which just means what they preload the memory with before they perform their testing. So they've used a checkered pattern. It's just a pattern of 1s and 0s alternating like a chessboard. They have used stripes, rows and columns striped with 1s and 0s, and they have used solid blocks of just all 1s or all 0s. Then they have also evaluated how many victim cells or rows per aggressor row that they could find. And they have found that for all manufacturers, there were up to 3 rows affected by one aggressor row and up to 9 rows per aggressor row for one manufacturer, manufacturer A in this case. Which is, of course, again, concerning that you can impact 9 rows with just 1 row of memory that you have access to. Now, the proposed solutions they have, the first solution they propose is to make better chips. Just as they do in the paper, I will not discuss this further. Their input on this is simply that, of course, if DRAM were improved and the chips were better, this will not happen. They don't have concrete solutions on how to make better chips, but they do have other solutions. The first one would be to use error correcting codes. But as we have discussed, there are multi-bit errors. So because of these larger multi-bit errors, it would be impossible or not sufficient enough to just use standard error correcting codes. And thus, you would have to use more complex error correcting codes, which would again introduce a larger overhead. Their next solution is to refresh more frequently. So as you have seen here, they would have to refresh at least 4 times as often for it to consistently drop off the errors. And that would again introduce, obviously, an overhead and a slowdown to the memory that is not as efficient. Their next proposed solution is to retire victim cells. So victim cells are the individual cells which have been tested to be flippable because as they have evaluated, some cells can never be impacted and some cells are very vulnerable. So on the manufacturing level, what they propose is, if this were done, that would of course be a large time investment because the manufacturer would have to test every single DRAM chip that they produce again, test them completely, test every single cell in the DRAM chip for vulnerability, test them sufficiently enough that they can guarantee that this cell is either not able to be disturbed or that this cell has disturbance errors. And then they would have to use some spare cells or even spare rows and just not use these rows, just after production manually disable these rows, that they will not be used by the memory and thus are safe. But that also increases production cost and there is no guarantee that there are enough spare cells. If they produce a memory chip and it has a lot of vulnerable cells, maybe they just don't have enough spare cells and thus they have to throw away the entire chip if they want to guarantee complete safety. On the consumer level, if the consumer were to have to manually test their own RAM they buy and then disable their cells, this would also not be very sustainable because it lowers the performance of the RAM that they have bought because a consumer could not just use additional cells within the RAM. That would not be possible because they wouldn't have access to such a low-level configuration of their hardware. And it requires end-user input. So it requires end users, be that companies or private people or also people developing the software that runs these modules, to perform this testing on every single RAM because it's not, it's very individual per the specific chips, right? So you couldn't just release a patch that disables row 1200 on every module of this brand because every single chip has to be tested individually. Their next solution they propose is to identify the hot rows during operation, hot rows being rows that are potentially trying to have a lot of activations to disturb their neighbors, and then refresh the neighbors so that the neighbors are more safe. Their charge is topped up again and they have more safety. They have argued in the paper that counters per row would introduce way too much area overhead. Having a single counter per row is just simply not sustainable. However, there are some hashing-based approaches, namely Bloom filters. There are also papers on this referenced in the original paper if you're interested in the specifics of Bloom filters. Bloom filters also have their own issues. They introduce hashing collisions, which is not a desirable effect and leads again to performance degradation. And they lower performance in general just by having more overhead. So all of these solutions that are proposed in the paper are not ideal solutions. They, however, propose a next solution, which is their own unique solution to this, and is called PARA. PARA stands for probabilistic adjacent row activation. And PARA has a probability defined as being much less than 1. And at this probability, every time a row is activated, one of the 2 adjacent rows will also be refreshed. Now, that would have to be physically adjacent rows. So this requires coordination with the memory controller to perform this efficiently. And they have tested para as a theoretical model with a parameter they set probability as 0.001. And they have tested both for runtimes of 64 milliseconds of just the same program and for 1 year. They have evaluated this in the table you can see below, with N referring to the number of activations that happen on the aggressor row. Now, for their research previously in the tables, the number of activations they had to have was 138,000 or upwards. So the middle column here is the starting to be representative, because at 50,000 activations, there's not really a lot of errors appearing. And even over 1 year, as you can see here highlighted, they had less than a 9.4 times 10 to the negative 14 chance of an error appearing. And the performance overhead of para running was at 0.197%, so significantly lower than the expected performance overhead of these other solutions. Para thus theoretically minimizes the errors with a very small performance impact, as they have proven in their simulation. Now, the paper concludes that first, there is a widespread appearance of disturbance errors in modern DRAM, modern referring to DDR3 DRAM in 2014, so it's not as modern nowadays. But on 129 modules they tested, they did find disturbance errors on, as I said, 110 modules, which is a sizable amount. They have found that the disturbances appear due to word line toggling and dense design, which enables these hardware problems to exist. And they have several solutions proposed, although most of them, they themselves argue they wouldn't fully work, including para, which promises a very low overhead at these 0.197% of throughput impact. Okay, so that was it for the paper.
Maybe we wait for questions if someone has questions.
Yes, does someone have questions on the paper?
Doesn't look like.
Okay, so I think most of you will have noticed the paper is about RowHammer, but at the time, RowHammer wasn't really known as RowHammer, which is why they refer to it as disturbance errors in the paper. The strengths of the paper, I think, are that they are the first to identify that this is a widespread problem in DDR3 RAM. So they have thoroughly tested this. They are also the first to identify the word line toggling being the cause of this. Previously, it wasn't fully known what exactly could have caused these errors. Now they have figured out it's specifically toggling. It's not reading or writing. It's nothing else. It's just word line toggling. They have reliably demonstrated this issue on a real system. And they have performed exhaustive testing. So they have, again, they have tested 129 modules across 3 manufacturers over diverse operating temperatures with multiple access patterns, with multiple data patterns. And all in all, that was just a very thorough examination of the available DDR3 RAM at the time. So I think that with this amount of testing, the conclusions of the paper are really solid. And I think they are right in saying that the disturbance errors, or as it is now known, RowHammer, was a serious problem at the time. Now, weaknesses. I do think the paper is very strong, but it has some weaknesses. First being that para, their solution that they proposed, their primary solution, does require the memory controller to be aware of row adjacency, which is something that is not as easy to do, because row adjacency is not something that the memory will just hand out for free. That would require cooperation between different companies to facilitate a solution that actually implements para in a way where it works. Next, there's no clear evaluation of the root cause. They say that it's the density of the DRAM, but they don't fully go into the electrical properties of the DRAM. It is a hardware problem, but they don't really go into the hardware much further than in their background. They don't examine the specifics of the DRAM, of why this could be happening. They don't talk about potential changes to DRAM structure that could fix this. None of that is evaluated in this paper. They only talk about mitigations and not about actually fixing the cause. And then the blast radius figure that I have shown and will show again soon is not accurate enough. So the figure down here is only discussed loosely in the paper, even though I think it's a pretty significant figure. And there is no deeper investigation on physical row adjacency and the actual impact of these aggressor rows on their neighbors. All they talk about is that these are addresses they get and that they might not correspond to physical addresses, but there's no effort in the paper to go further into exactly what the physical adjacency could be and if all of these rows that are further than one are actually physically adjacent or not. They don't examine this at all. Yes. Okay, so for my discussion, the first discussion question I have for you guys is, what have DRAM manufacturers done since? So this paper was released in 2014, right? That is over 10 years ago, 11 years exactly. So a lot of time has happened.
I think they introduced something called target row refresh. I don't know if that was already in DDR3 or not.
Yes, so TRR, target row refresh, was not in DDR3. It was introduced in DDR4 as one of the first fixes. So I think, yes, that's even my next slide. So one of the things they have introduced is TRR, target row refresh. It was implemented for DDR4 and onward. And what it does is it refreshes only target rows that are being identified as under attack. It does this fully in the memory, so TRR is only implemented inside of the memory by memory manufacturers and was their one of their first attempts to mitigate this problem in DDR4. And it doesn't require any cooperation with the memory controller and the CPU due to being isolated to memory. However, it has been broken many times since and has been shown to not fully mitigate RowHammer, or in some situations not mitigate it at all. Any further ideas what manufacturers have done? Okay, so there are of course many other mitigations that they've tried, but there is one that has also been tried a lot, which is called PRAC. PRAC stands for per row activation counters. It was implemented for DDR5 and it counts activations on request. So this is now a cooperation between the memory and the memory controller in the CPU, where the manufacturers have sat together and tried to come up with a solution. And what PRAC does is it's more of a loose standard that has been implemented in many different ways in research and in practical attempts. All of these implementations show some promise and some success, but also all of them introduce some overhead. So none of the PRAC implementations so far have been fully mitigating RowHammer without any form of overhead, which is of course still not ideal because of the performance impact. My next question would be, what about further mitigation by the memory controller? So what else do you think the memory controller could contribute to this problem? Or should they even contribute to this problem, maybe?
Maybe the memory controller could also have some kind of view of how many requests are going through to a specific row, and then maybe move that row to some kind of row jail where all the RowHammer rows can be copied to.
Yes. So that is a good solution, good idea that has also been tested. That would be the migrating of aggressor rows, and that is one of the potential solutions that a memory controller could implement. So another one would be stalling of suspicious memory accesses, just slowing down any process that is showing a significant amount of accesses to the same address over and over. Of course, this would degrade performance of this process and could potentially target processes that are not actually being harmful or trying to be harmful. You could detect the hammering and migrate the victim rows, or migrate aggressor rows, as you have proposed. However, all of this leads to undesired CPU overhead. And it, again, potentially requires manufacturer cooperation almost industry-wide. There's a paper on this called Self-Managing DRAM, which argues that since these disturbance errors are an issue in DRAM, it should also be solved by DRAM. And some of the solutions that we have discussed here require cooperation, such as PARA, PRAC, the migrating of victims. Others don't actually require this cooperation, such as the stalling or the migrating of aggressors. They just are performed by the memory controller, but it's still undesired CPU overhead that affects the CPU performance. So all of these mitigations are a burden on the CPU manufacturers, where they have to fix issues that they themselves have not produced, where they have to fix issues of the memory manufacturers, which of course is a difficult situation to put the CPU manufacturers in. This problem is, as we can see, a fundamental DRAM problem, and some people are arguing, for example, the paper that is cited below, that this should be solved by DRAM manufacturing instead of just mitigated by other people, other processes. Now to my last question, do you think RowHammer is fundamentally unfixable? Okay, so my thoughts on this are that DRAM is getting smaller. It's running at higher frequencies. It's required to have competitive performance for profitability. So all the mitigations that impact performance could also always impact sales. And thus, my conclusion is that with the current DRAM architecture, it can fundamentally not be fixed. It can be mitigated, but if we want to truly fix it, we would have to come up with a completely different memory architecture that just doesn't have this issue. Because current DRAM, the way it works, will always be vulnerable to these electrical hardware phenomena. Okay, that was it from me.
Okay, does anyone else have questions or discussion points that they would like to bring up?
Do you know if PARA is actually used in some real DRAM systems?
Not completely. So I haven't found any commercial systems that implement it to my knowledge, but I'm not aware. It's also possible that they are using it and are not disclosing that they are using it. That is often done with these mitigations, just to further increase the security. If you don't know what security measures are in place, it's harder to crack them.
There are indeed some systems that implement something like PARA, and you can even configure the probability from your boot configurations and so on, but it's not acknowledged. I think also it's not advertised. But yeah, there are some probabilistic mitigations in some of the systems that we use today, or we have been using since, I guess, since this paper came out.
Okay, then I think we're done with the first part, and we can be back and start with the second presentation at 5:05. Okay.
Yeah. Okay.
Yeah.
Oh, perfect.
You can always press that button to turn. And have a button, like third person. Should we get started? Okay, hello everyone. Welcome to the second session of this lecture. So today we have Jonas. He will present PuDHammer. So his last year of his master's, electrical engineering master's, and in his free time he liked to bake, hike, and read sci-fi novels. And he's mostly interested in hardware security and robustness related research. So feel free to start, Jonas.
All right, thank you very much for the introduction, and thank you, Kim, for the presentation. It's a lot of good ground for this presentation, I feel. I'm going to present to you PuDHammer, an experimental analysis of read disturbance effects processing using DRAM in real consumer DRAM chips. So the motivation is nowadays processing using DRAM enables us some more efficient computation, right? We move some computation closer to the memory or in the memory. And this can be done with unmodified consumer or on-the-shelf DRAM chips. And the way they do processing using DRAM with these chips is that they activate multiple rows at the same time or in quick succession. But the RowHammer, as you saw before, requires us opening and closing a row in quick succession to induce some read disturbances in neighboring rows. So the question is, if we have some processing using DRAM, right, and it uses multiple row activation in quick succession or in simultaneously, how does this influence our DRAM read disturbances, right? So basically, we're using processing using DRAM to hammer the rows. So to explain this, they did an experimental study. They tested over 300 DDR4 chips. Those were all non-ECC from 4 major manufacturers, and they observed an up to 158 times reduction in the minimum count to first bit flip. So when we hammer a row, we need to access it a certain number of times, and then at some point we will observe a bit flip in the neighboring rows, and this will be our hammer count. Okay, so they also found that it bypasses the current DDR4 mitigation. So that would be TRR. TRR is not standardized. So all the manufacturers could have different implementations of TRR, but you'll see for which one it was effective later. And they have achieved 11,000 times more bit flip than conventional RowHammer efforts. We'll get into that in a bit. They also propose an mitigation, which they call adapted per row activation counter, PRIC. Unfortunately, this new mitigation incurs a very high overhead of nearly 50%, I think 48.26, yeah, which the authors of the paper call prohibitive. And I agree. So for the structure of this presentation, I'm going to give a quick refresher. I will go through the parts that Kim has already mentioned a bit quicker, so I don't bore you too much. So we do the quick processing using DRAM refresher as well. And afterwards, we're going to go towards the testing infrastructure they used. So what was the testing setup? What was tested? What parameters were varied during the tests? Afterwards, we're going to look at the results of the tests. of consecutive multiple row activation and simultaneous multiple row activation. And we're going to conclude and then hopefully have a quick discussion. Okay, so let's give us a quick refresher why we are interested in processing using DRAM. So on modern computing systems, you have your memory, right? And you have some kind of processor. This could be whatever. You want to move data from your memory to your processor, right? And as I said, this processor could be anything that is related to processing. It could be a CPU, some accelerator, maybe even an FPGA. And studies have found that this data movement that is occurring and needed for the system to function incurs up to 60% of the total system energy. Right? So 60% of the total system energy is needed to move the data to where it needs to be. And since we also need to wait for data to arrive before we can do any computation, the data movement is a big bottleneck right now. So processing using DRAM promises us to alleviate that bottleneck a bit by shifting the processing closer to memory, so there is less data movement needed. Yeah, I'm going to give you a quick recap of the DRAM architecture. Kim has already mentioned it. So let's say this was your DIMM, your DRAM module. It is split into, so each of the chips is split into several banks. These banks are composed of subarrays. And then if we look into one of those subarrays, you'll see the familiar image from earlier, where we have our DRAM row here, the bit line, as you saw, the word line, and the DRAM cell, if you remember what it looked like from earlier. And down here, we have our sense amplifiers, which help us read out our DRAM rows. Okay, so there's a couple operation primitives that we need to look at to understand what DRAM does. Kim has already mentioned them, so I'm going to speed through this a little bit. We have the activate command, which reads the row contents into our sense amplifiers. Once they're in our sense amplifiers, we can do some operations on them. We can read from them, we can write to them. And then in the end, we need to pre-charge the cell because DRAM readout is a destructive process. The charge needs to be reinstated. For all of this to work, the manufacturer has a data sheet, and on the data sheet, they're going to tell you how much time you need to wait in between these DRAM commands so that they all finish before you issue the next one. Right. But processing using DRAM specifically violates these timings to achieve some effects that they find desirable, such as the in-DRAM computation. So let's look at how they do some of these primitives. We're going to look at two effects that they can achieve by violating these timings today. One is consecutive multiple row activation. The other one is simultaneous multiple row activation. We'll get to that in a bit. So for consecutive multiple row activation, you issue your activation command, then you pre-charge, and then between the pre-charge and the activation of your destination row, right, you're going to violate the timing. And it's going to be a lot shorter than what the DRAM manufacturer would write on their data sheet. And this way you can copy the source row to the destination row, right? So these rows are activated in very short succession, and the charge basically gets written into our destination row. So for the simultaneous multiple activation, the process is kind of similar, but there's a bit of a difference, and I'll explain it in a second. So we do the same thing, and we violate these timings. These are even shorter. So the delay between these is even shorter than in the previous example. And because of how the row decoder is manufactured, depending on which rows you activate here, other rows will also be activated because you violated the timings. So you can activate 2, 4, and then powers of 2 up to 32 rows at the same time, simultaneously. And this will be, we will discuss this later, how this affects the effect of RowHammer, or the read disturbance effect. So you already know what RowHammer is. I'm going to tell you again. So by activating and closing a row multiple times, short succession, we can get read disturbances in neighboring rows. That's all you need to know for this paper to understand. So if the single row activation, where we activate a single row in quick succession, what will happen if we activate multiple rows at the same time or in very, very quick succession, because we violated those timings? To answer this question, they made a testing setup which gave them very fine-grained control over the timings for the DRAM. It looked like this. So down here you can see a PCIe connection to the host machine, which connects this FPGA board to a computer. On this FPGA board, you have your DRAM module, and the FPGA board is loaded with a DRAM bender, which is a software or FPGA programming also developed by the Safari group, and it gives you very, very fine-grained control over what happens on the DRAM, what commands are being sent. So otherwise, this would not be possible, right? If you plugged in your DRAM into your regular old computer, it would be a lot harder to get this effect, to violate the timings. Also, on the DRAM module, if you can see it, it's wedged between two heater pads, which are connected to a temperature controller, which gives them some accuracy on what the temperature of the DRAM chip is. So this way they can vary the temperature and then see what the effect is on the read disturbances effects. Okay. Oh, should have clicked. So the chips that they tested were by 4 major manufacturers, SK Hynix, Micron, Samsung, and Nanya. They tested, as I said, over 300 different chips. Not only that, but the chips were also from different die revisions, which means that they were from different generations of chips. This is over, so not just a single manufacturing revision, but different versions of this chip. So there are, it's a bit of a spread, also in density, going from 4 GB all the way to 16. So the variety in these chips is pretty good for a study like this, and there's a lot of chips to be tested. The parameters that they tested for was obviously the rows for our consecutive multiple row activation. All the rows in a subarray were tested as victim rows. The timing parameters were also varied. In this case, for all the figures that I will show, they used 7.5 nanoseconds between the precharge and the activate. But they varied this, and this was what worked best. The data patterns they used ranged from all zeros to all ones, and then some checkerboard patterns, so alternating. And the temperature ranged from 50 to 80 degrees C in 10 degrees increments. But for all the figures that I will show, 80 degrees C will be the one that the DRAM chip was at. They chose 6 subarrays per bank per chip, testing 1 chip for each DIMM. And as I said, all the rows, and they chose those 6 subarrays in the following manner: 2 in the beginning of the chip, 2 in the middle, and 2 at the end. They determined the minimum hammer count first using bisection, the bisection algorithm. And much of this does not change for their methodology for simultaneous multiple row activation. The things that do change is which row addresses were probed and the timing parameters. So here, the row addresses, they chose 100 groups each for varying amounts of simultaneous multiple row activations. So if you remember, the simultaneous multiple row activations can go from 2 to 32. So it was 100 groups each. And also because now we do a different method, we also need to change the time parameters. So for all the figures that I will show, this will be our timing. Okay, so let's continue to the effects of consecutive multiple row activation. So quick refresher. This is what we had. There's 2 prime methods that we can use to do hammering with those. First is a double-sided, where we have a victim that is sandwiched between two aggressors, and a single-sided, where we make sure that our victim is not sandwiched. Right? So we move our other row somewhere else where our victim row will not be sandwiched. Okay, let's look at some of the results. So I will walk you through this graphic. So down here you have the percentile of rows and the HC first change on the y-axis. So this is in comparison to standard double-sided RowHammer. And these figures are for double-sided consecutive multiple row activation. So for example, this would be 99% of victim rows, right? Or 50%, or right, this would be the line where nothing changes compared to double-sided RowHammer, right? You get it. 50% reduction and so on. So we can see that 99% of victim rows, they have a lower hammer count first compared to double-sided RowHammer. And if we look at the lowest hammer count first, you'll also be able to see that for each manufacturer, or for every manufacturer, our consecutive multiple row activation is significantly better. Right here, it is a bit hard to see, but if you look at the numbers, you'll see that it is a good bit better. Okay, so COMRA does worsen our RowHammer across all manufacturers, right? But it's not that that bad. If you look at the numbers for Micron, maybe it is pretty close. So they also use the temperature as a variable, and we'll see another figure later which shows this a bit better. But you'll be able to see that for increasing temperature, our hammer count first, which is, you know, things get worse when this number is lower, right? Because we need less hammerings before we can actually get a bit flip. You'll be able to see that for 80 degrees, it is the lowest for all. Okay, let's look at the simultaneous multiple row activation. We can also do two ways of hammering, single-sided and double-sided. So here it's the same principle. We have our victim row and it is not sandwiched. And then for double-sided, it is sandwiched. And for this particular example, we have a SIMRA 4 because we have 4 aggressor rows activated simultaneously. Okay. I have to note that the paper stated they got the simultaneous multiple row activation working on ISCA Hynix chips only. So they tried it on all of the manufacturers' chips that they had. And this one was the only one where it did work. So as I said, there's some interaction with the row decoder that makes simultaneous multiple row activation possible. And this only worked on SK Hynix. So all of these figures will be for SK Hynix only. The same as for COMRA, we have for SIMRA, 90% of victim rows have a lower hammer count first. But SIMRA is significantly worse if you look at the figure compared to the other one, in that we also have 25% of rows with 99% reduction of hammer count first. But I'll show you a side by side. But first, let's look at the lowest hammer count first. This is the purple one is RowHammer. And down here, you have the simultaneously activated rows, and you'll be able to see that you need very, very little hammerings before you can get a bit flip with SIMRA. Compared to COMRA, you can see here that it is much, much more effective. Keep in mind, this is for SK Hynix only, so this is the figure that we're interested in right here. They also did the analysis over temperature, and I said earlier, this one's going to be nicer, and you can clearly see that there's a downward trend and how many times we need to hammer before we get a bit flip, which means that it's also worsening. So if you have a hot data center, maybe you're going to be less secure if you use this. Let's do a little trip and look at the simultaneous multi-row activation when there's TRR enabled, so we have some kind of defense. So this is a standard RowHammer. You can see as the number of our aggressors increases, we get more bit flips. And then here with TRR enabled, you see the double-sided is the most successful. For SIMRA, you'll be able to see that it is not very much impressed with the effort of TRR. So the reduction in bit flips from non-TRR to TRR is very small. And we have over 160,000 bit flips still with the 32 simultaneous activations, whereas for RowHammer we had less than 60 for our most successful pair. Yeah, on average, this is a big increase, 11,340 times more bit flips. Should send you worrying about your data center, I guess. Okay, so the key takeaways for me were that both COMRA and CIMRA are much more effective than your standard RowHammer. CIMRA is actually extremely effective at reducing this hammerings needed until you get a bit flip. And they're both influenced by temperature. Higher obviously means that they have more bit flips at some point. And CIMRA bypasses TRR very effectively. There's as I showed you, there's a very little decrease in bit flips achieved once you go and enable TRR. Okay, let's continue to the proposed mitigation. So the paper actually proposes a mitigation and evaluates it using a simulator. So the Paro activation counter was already mentioned. I'll just refresh your memory. So the principle is that we count each row activation, and at some point we'll reach a threshold that we have determined. And if that threshold is reached, we will refresh all the neighboring rows, right? So our victim will at some point be refreshed if the counters for A or B reach that threshold. The problem with this is that it's, for our case, expensive and slow, right? We have a lot of activations. We have activations that are happening at the same time. So these counters will need to update, and then this will need to update, and they're going to wait on the counters until we can do another memory access. Also, we need some more circuitry, right, in our circuit to enable this. So in the paper, they propose a performance-optimized weighted per row activation counter. Performance optimized here means that instead of consecutively updating all the counters, they updated them at the same time. So this adds some area overhead, but yeah, this was not, since they simulated it later, this was not much of a concern. And they also increment the counter by a weighted amount. So for CIMRA and COMRA, the weight was calculated like this. You take your hammer count for standard RowHammer, and then for the hammer count for CIMRA, and then you get the weight that you add each time you observe it. And you can see here, this was their evaluation. The dotted line is your standard no RowHammer mitigation, so bare bones. And then you have the orange one is the one that I just talked about, which has the weighted counter, and this one does not have the weighted counter. So these numbers down here is how many times, so every 125 nanoseconds, for example, for this one, we would execute back-to-back CIMRA and COMRA operations. So over here, we have the very high load, and here we have the very low load. And on average, this incurs an overhead of 48.26%, which is too much. Basically, it negates a lot of the speed up that we would achieve using processing using DRAM. So the bad news is that PuDHammer shows that processing using DRAM is extremely, the memory is extremely vulnerable to having its timings violated, to having multiple rows activated consecutively at the same time. The proposed mitigation is pricey. So whatever speed up you have, it needs to be good before you want to look at this mitigation. The TRR RowHammer mitigation is very weak against CIMRA. The reduction was, I think, less than 10%. And there was a clear temperature relation, which, you know, now you need to implement temperature control to be secure from RowHammer, or PuDHammer in this case. But the good news is, now that we know about it, and it is very well characterized, there's a lot more in the paper in terms of characterization that would not fit in this. I'll tell you about it later. Now that we know about it and it's well characterized, there can be a lot more work into it, right? Now, at least there's a good foundation now. And since processing using DRAM is not yet implemented into consumer devices, it is still in its academic stage. So there's still a good amount of time to work on better mitigations. I think for me, the strengths of this paper were that the characterization of the processing using DRAM operation was very exhaustive. 316 chips is a lot, and characterizing all of those takes a long time. So this is very solid groundwork for any future research. They did very in-depth analysis. So I showed you the temperature and the HC first and how many bit flips it got. But they also tested data pattern and timing. So with timing, I mean that they changed the delays between the commands. And they also had some good results for those. So this adds to the foundation that they are building with the large chipset size. And this is the first research into this direction of read disturbance effects. So in the direction of processing using DRAM, how they do it. This is the first one that shows how vulnerable it is. They also clearly demonstrate that there is the need to do something, to implement some kind of mitigation, because it bypasses TRR. So whatever is already in the DRAM is clearly not enough. So for my perceived weaknesses, I think that the worst PuDHammer method, which was the simultaneous multiple row activation, it only works on one vendor, which was SK Hynix. So that makes the findings a little bit weaker. It would be nice to see if there are other vendors that have the same kind of logic in their circuit that would enable simultaneous multiple row activation. They had some limited spatial testing because they had to choose 6 subarrays per bank per chip. Otherwise, the workload would become too large, I think. There's no efficient mitigation inside. They proposed one. Obviously, it's not efficient. But I think making a mitigation that is efficient is very hard, especially for this, because there's a lot of things that the manufacturer maybe didn't intend. And also there was no DR5 testing, but I do have to say the authors did have a section at the end where they discussed if this will work on DR5, and the consensus was that it should. Okay. We will continue to the discussion if you have any questions.
So from a manufacturing standpoint, you said at the start that the timings are somewhat violated by this PuDHammer due to PUD. Would it even be possible to do this without the FPGA? Would it be possible for like a user level program or any type of program on a computer to perform this type of attack maliciously without being able to violate these timings?
I think with a consumer grade PC, I would imagine it to be very, very difficult, if not impossible. I don't think it gives that fine-grained control over timings. So yeah, it would probably not be feasible.
Maybe I can answer that question also. So what we are trying to show here is for future, basically, because there is no processing using DRAM enabled DRAM chip. And we don't know if they're going to design the DRAM chip as if now. So we just wanted to show that there is something here, read disturbance. You know that from RowHammer, yes, it could induce bit flips. But with these operations, it's getting very vulnerable to the DRAM chip. So in the future, if you're going to design your DRAM with the capability of performing this in DRAM operations, you need to take this into account and you need to somehow have a mitigation, because this would make processing using DRAM basically almost impossible, right? So this is like a warning, or like we should be cautious about these kind of things. But yeah, in today's systems, yes, you cannot do that because there is no available chip for that. Good question, though.
Okay. Yeah, let's continue to the discussion section. I'll keep it short. Imagine you are tasked with getting new hardware for a data center, and somebody asks you, or you look up online and you see there's one beautiful server and it has a processing using DRAM enabled. It's 2 times faster, and obviously a regular one. Which one would you get for the data center? So, I mean, there's a couple of things to consider, right? There's some kind of security speed trade-off, right? We've talked about it. For sure, if you're going to get the PuD enabled one, maybe there's less security, maybe there's more speed.
I mean, it's also highly dependent on the workload that you actually have, because not every program is able to use processing in memory or using memory. And then you would have to write your software such that it could use it. Mm-hmm. And you would have to potentially have higher costs for processing using DRAM, because those are like specialized chips that are not standard as of now. So you would probably have to mix and match if you would want to use processing using DRAM, because most of the consumers would probably not want it enabled, or would not even be able to use it with the software they would currently want.
Yeah, for sure. No, there's obviously the debate: how transparent should it be? How much detail you want to give to the programmer in the end, right? There's also some kind of cost energy. This processing using DRAM might make your system more efficient. So maybe this could also be a concern. I don't know if there's any. Are there any processing using DRAM chips that are commercially available these days? Oh, okay. Probably for the better for now. Anyone else? Does anybody want to argue for processing using DRAM chips? Okay. For my second day discussion question, I have if you think that DDR5 is safe from PuDHammer. I already said that the authors of the paper think that it is not, but if you have any other opinion. Or maybe why you think that it is also not safe.
Well, I can play along. It's likely more unsafe given that it's more dense. But we don't know because we haven't tested this yet.
Sure. Yeah. Yeah, but it would make sense for it
Very
also.
likely that it is, though.
Yeah, because obviously it has this going for it, double the rate of refresh, but it's offset by it obviously being a smaller, faster. It's a denser technology, and both Simra and Comra had a very low hammer count first, right, until they got a bit flip, and even with the double rate of refresh, it might not be enough. So, yeah.
By using double the refresh rate, they probably, for even enabling processing using DRAM, would also have to cut the rates at which they activate and the rows to use processing using DRAM. They would also have to cut them in half or so, right?
I'm not sure what happens with the timings once you have a. I think.
I know, right? It's only the refresh.
Separate.
It's not the activation time that's halved.
Yeah.
Yeah. Right. Okay, but even so, you would still have to, probably because DDR5 is like faster, you'd probably even still have to make the timings even shorter to make processing using DRAM even possible. And since you're violating the timing parameters, I mean, obviously the timing parameters the manufacturer gives you are there for something, for security. And if you violate them, then you have a high chance of making something wrong.
Yeah, for sure. I think that's a very good point. I'm not sure if the timings are impacted by that much. They probably changed, but they probably didn't have.
So interestingly, DDR5 internal timings are the same.
Okay.
DDR3 is the same. It's not going well for them. The latency over there to issue the commands are the same.
Okay.
But the IO and all the other things are getting faster. Yes, that's true. So, but as I said, like here, what we observe is really coming from processing using DRAM operations. Not so. This is a valid concern of you're doing something wrong according to datasheet, right? So you're violating it. You're doing what is out of spec. So we had a lot of actually experiments that we didn't put here because it's like it will be 30 pages of paper that we made sure that this is really the processing using DRAM. One thing is that the bit flip directionality in the paper that we show that it is very different than RowHammer, but it is very close to row press that you wouldn't expect. So for example, 1 to 0, so you flip the bit, but flipping 1 to 0 is much easier than flipping 0 to 1. So this shows some characteristics. But for example, when you do double-sided RowHammer, usually it's 0 to 1. So it's exactly the opposite of RowHammer. It's close to row press. We don't know why. But we believe that this definitely needs like a circuit level, TCAT level simulation to understand what's going on, because you're doing something fundamental different, right? So in RowHammer or row press, what you do is you activate one row, you close it, you activate another. So there is no such a time that both of them are activated at the same time. But here we activate them at the same time. So fundamentally something is different, and unfortunately we couldn't, let's say, find a way to understand this because it's like a black box. You just have the DDR module and you don't know the parameters or anything. So there are some groups, actually, there are some efforts to understand those read disturbance mechanisms for RowHammer and row press. And we can only hope that they will get interested on this and try to figure out what's going on as well. But I believe if you're moving forward to enable this processing using DRAM operations, you would somehow needs to specify this in the timings, right? So you need to say that I will issue not act. So what we do here, activates, violate timing, per charge, violate timing, activate. Instead of doing that, you need to have like, do SIMRA command, and it should internally do that. So in that sense, you wouldn't violate the timing. But since the physical mechanism activating two rows at the same time is still there, we should at least, I think, expect that this effect will be there still. Yeah, it's a bit long answer, but yeah.
Yeah, I mean, it would probably be a lot cheaper to use existing DRAM technology, right, for processing using DRAM than to make an entirely new one, just, for that issue. So it would be nicer maybe to have something that works out of the box already. Okay. Yeah, that's what I already said. So the last one, why did the simultaneous multiple row activation defeat here R? And I didn't show it, but the consecutive multiple row activation also did better, but to a much, much lesser degree.
Is it possible that the TRR was just overwhelmed with counting all the simultaneous rows and then couldn't track anymore which ones are being targeted because it's just so many rows at once?
Yeah, it could be that there was some that it missed to count some of the rows. That's for sure. that missed some accesses. Yeah, and that would definitely make the performance of TRR worse, right? If it doesn't have full information about which rows are being activated, that would definitely make it worse. Yeah, very good. Yeah, I have the same thing, basically. So you activate more rows simultaneously with SIMRA, more than the TRR can accurately track, because it doesn't know about it. This mechanism, how we activate them, might not be visible to TRR. Also, as I said before, the RowHammer threshold is much lower, and also the TRR will look at how many times some rows have been activated and then decide if it's going to need a refresh or not. And since this is a much lower threshold, it might also miss it. Right? This is coupled with how it doesn't track them correctly, I guess. Yeah. Okay. If there's any more questions, I'm happy to answer. All right. Thank you very much.
Questions? Okay, then.
Then I think we can conclude. Thank you all for attending.